modeling optimization problems, which is also known as linear programming. So McDonald's optimizes, and they optimize their input and their output. So they want to make money on what they are doing, so they look closely at calculations to make sure that what products they're selling at a fair rate, but also what makes them money. And any of those products, any of the material, they need to make sure that they're getting them at the lowest price so that they can make profit. So the expenses for McDonald's would include the raw material, cost to make the food, cost of the building and utilities, shipping, and employee wages. And the income is, well, you guys. So McDonald's has mathematically worked out what price the food should be, how big the restaurant should be, how the seats are to be designed, what color the restaurant should be, how many restaurants should be in a town or a city, and many, many more things. So in order to ensure that they are making the largest amount of money that they can make is called optimization. So let's look at this example here. A florist is ordering bracken fern and baby's breath for bouquets and centerpieces. No more than 100 stems of baby's breath will be ordered, and more than 100 stems of bracken fern will be ordered. The florist has space to store no more than 250 stems in total. Are each of the following a combination that she can order? Explain. So here there is a couple restraints here. We have no more than 100 stems of baby's breath. So if we look at our baby's breath, no more than 100. So I'm going to see if there's any of the combinations that have over 100 baby's breath, and it's this guy here. So I'm just going to cross him out. He can't happen. More than 100 stems of bracken fern will be ordered. So I'm going to look at my bracken fern. Is there any that is under 100? If so, I get rid of them. So this combination is gone. That's it. And the florist has space to store no more than 250 in total. So now I'm going to look to see these combinations and see if any are over 250. This first one is good. The next one adds up to 200. That's good. Next one is also 200. That's good. This one we can't have. We can't order half a baby's breath or half a bracken fern, so this is out. We can only deal with whole numbers. And my next one, 100 and 150 together, that is 250, so that would be good. So all of these are combinations that we could possibly have, so those 4. And there is one that is going to optimize this florist's in regards to space that she has available on sales, and that would be this last one here, because it adds up to perfectly 250. All right, a toy company manufactures 2 types of toy vehicles, racing cars and sport utility vehicles. So we have SUVs. Because the supply of material is limited, no more than 40 racing cars and 60 SUVs can be made each day. However, the company can make 70 or more vehicles in total each day. It costs $8 to make a racing car and $12 to make an SUV. There are many possible combinations of racing cars and SUVs that could be made, and the company wants to know what combinations will result in the minimum and maximum cost, and what those costs will be. So how can the situation be modeled? So what are 2 variables in this situation? Well, we can label them as X and Y. And we can let X be the racing cars, just because it came first in my problem. And Y can be SUVs. We're going to write a system of 3 linear inequalities to represent the following conditions. So the total number of racing cars that can be made. And if I go back, it says no more than 40 racing cars. So my racing cars, X, has to be less than 40. And it can be equal to no more than 40, so I can be 40 and under. The next question is the total number of SUV vehicles, and it tells me 60 SUV vehicles. So no more than 60 SUVs. So Y is less than or equal to 60. And the total number of vehicles that can be made, and it told me that it can make those racing cars and SUVs, it can make over, oh, wrong way. It can make over 70. Just to double check that, let's see. The company can make 70 or more. So 70 is included. What do you know about the restrictions on the domain and range? So we are dealing with cars. We can't have half a car. We can't have negative cars. So X belongs to whole numbers and Y belongs to whole numbers. Another way that we can represent that, we can also include the following restrictions: that X has to be greater or equal to 0 and Y has to be greater or equal to 0. And that just also shows that we have to be those positives. So including in that whole numbers. So we're going to graph the system, choose at least 2 points in the solution region. Okay, so we're taking this one, and this one. Those 3 linear inequalities. Okay, so there are all 3 of them. Now notice that the numbers that I have is 40, 60, and 70, and my graph over here, it shows that it goes up to 10. So I am going to make each box, let's see, what is a nice one that will fit? Each box is going to represent 10. So this is actually 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Same with over here. There. Now that'll fit. So when I graph this guy, X is less than 40. On my X number line, I'm going to find 40. And there is no Y value. This is one of those situations where I have that line going straight up and down. It's a solid line because 40 is included. I want to be less than 40, so I'm going to be to the left. And if you weren't exactly sure, you can check a point such as 0, 0. And we get that 0 is less than 40, and that's true. My next one, Y is less than or equal to 60. So my Y axis, I find 60. It's another solid line because Y could also be 60. And Y is less than 60. I'm underneath. Also, you can check a point, and you find that the point 0 and 0 does satisfy the inequality. So I am below. Now, I'm going to graph X plus Y is greater or equal to 70. I'm going to move my X over, so I'll subtract both sides by X, and I get Y is greater or equal to negative X plus 70. Plot my point at 70, and my slope is negative 1 over 1. Down 1 over 1, down 1 over 1. And this is another solid line. I have to be, well, it says X plus Y is going to be greater than 70, so I am going to expect to be above the line. But if you weren't sure, check a point. We can check 0 and 0. And we get that 0 is greater than 70, which is not true, so I'm on the opposite side. So I do have a shared region. that is in this region right here, and I can dot those possible solutions. So it says choose at least 2 points. This guy right here is a point. This is the point 40 and 30. This guy right here in the center can be a point, which is the point 30 and 50. So there are 2 possible points. And here would be the answer. All right, what quantity in this situation needs to be minimized or maximized? Write an equation to represent this. So if I go back to that slide about the cars, it tells me that it costs $8 to make a race car and $12 to make an SUV. Now, as a company, I want to not spend a crazy amount of money making my vehicles. So it wants me to find the minimum and the maximum cost. And I'm going to use these values here, these dollar amounts. So it says $8 to make a racing car, and we can represent that as 8x. And it's $12 to make an SUV. We can represent that as 12y. Now together, if we add them up, that's going to equal our cost as a company. So that would be what we call an objective function. So that once again was our 8x plus 12y is equal to our cost. So that's in our equation. An optimal solution is a point in the solution set that represents the maximum or minimum value of that objective function. So there is an optimal solution that has the best outcome. Which point would that be? So here is the answer to those racing cars and the SUVs, the graphs for that. Here was our objective function. They just changed those variables to S and R. We can put them back to what we had, 12y, 8x. And you can start testing points in this region to find what's going to give you the best answer. If you want me to ruin the surprise, test your corners. They're called vertices. Plug in those 3 corners into your objective function. They're going to give you the maximum or the minimum. So if you wanted to go ahead and try that, we can test. Let's see, I'll just number them off so we don't lose count. 1, 2, 3. If I was to plug in point number 1, 30 and 40, my x value is 30, my y value is 40. Also, I probably should have had a calculator nearby. I didn't bring myself a calculator. Okay, so that's our first one. If we plug in the second one, 60 and 40, in place of y, I will put 40. And in replace for x, I will put 60. And then number 3, the point 60 and 10. So in replace of y, I'm going to put 10. And in replace x, I'm going to put 60. So, as a company, I want my cost to be the lowest as possible. That would happen at this point here.